Alright, so this is going to be 4-3. It's a longish section, so bear with me. But there's a lot of calculator stuff in it, which makes it kind of nice. So before I jump into the section, really the title of this section is roots. I probably could have called it radicals. I kind of maybe use these words interchangeably when I'm lecturing. So this is a square root symbol. I imagine you're somewhat familiar with that. Doing like this, I call this a cube or cubed root symbol. If I change this to a 4, I call it a fourth root. If I put a 5 in there, it's a fifth root, and it goes on forever. I can actually spell fifth. Notice in the square root there's not a number in the little cup. That number, if there's no number written there, it's assumed to be a 2 as opposed to a 1. A lot of times in mathematics, if we don't write a number, it's assumed to be a 1. Each of these numbers, the 2, 3, 4, and 5, the 2 that's assumed and not written, the 3, the 4, and the 5 is the index. So for the square root, I say it has an index of 2. The cube root, I say it has an index of 3. The fourth root, it has an index of 4, and the fifth root has an index of 5. Square root asks the question, what positive number times itself twice equals the number under the radical? So for square root, it technically wants a positive number. The question this is asking is what positive number times itself twice. I guess the times itself is probably the twice is implied. Equals, and I'll call it properly the radicand, which is the number under the radical. So radicand means the number under the radical. If I put a number under here, like 9, I would read this as the square root of 9. And because positive 3 times positive 3 equals 9, the answer to this, the square root of 9, is equal to 3. Even though negative 3 times negative 3 also equals positive 9, the square root symbol, it wants we call the principal square root or the positive square root. Calculator does square roots real easy. I don't need to worry about the 2. If I want to do the square root of 9 on my calculator, I type the square root key, which is right next to the x squared key, type the number 9 and hit enter, and my calculator knows that is supposed to be the number 3. If I bumped up the difficulty to a cubed root and threw a 64 under it, cube roots don't specify positive or negative numbers. Cube root of a positive number is going to be positive. The cube root of a negative number is going to be negative. So this cube root, when the index is odd, 3 is an odd number, it doesn't care. It doesn't specify positive. So this means what number times itself 3 times equals the radicand 64. The answer is 4 because 4 times 4 times 4 equals to 64. More often than not, if you're not teaching math, you don't know the cube root of 64 is 4 because you don't know that 4 times 4 times 4 is 64. So, to do that on my calculator does have a cube root feature, and the cube root feature is right above the square root. If you look right above your square root key, you can't see it on my calculator because it's written too small, but if I hit the shift button and the square root key, it gives me a cube root. And if I just type in the radicand of 64, my calculator will tell me that that's equal to 4. fourth root, because this is an even number, we say it has an even index. It's also calling out a positive number. This asks me what positive number times itself four times equals the radicand, which is the number under the radical. Let me throw a big number under there. So if I want to find the fourth root of 625, that's asking the question, what number times itself 4 times is 625? And the answer to that question is 5, because if I go 5 times 5 times 5 times 5 4 times, I get 625. So that is the answer to the question. That's not, probably common knowledge. So how do I get a fourth root on my calculator? It's not terribly hard, but there isn't a pre-programmed fourth root. There's a pre-programmed button right above the X with the square key that allows me to enter any index that I want. So if I want to do the fourth root of 625 on my calculator, I hit the shift button and then the X with the square or the exponent key, and it gives me the ability now to type in whatever index I want. So I'm going to type the number 4. I'm going to arrow over and type in 625. And so I get the fourth root of 625 is 5. And then the last thing I wrote was a fifth root. This, again, doesn't care about the sign of the number. It just asks me what number times itself five times, as opposed to 4, 3, or 2 times, equals the radicand. I don't know many fifth roots. They won't come up a lot in this chapter. If I asked you to do the fifth root of 32, it asks me what number times itself 5 times is 32. The answer is 2, because 2 times itself 5 times, 2, 3, 4, 5, messed up. 2 times 2 times 2 times 2 times 2. 2 times itself 5 times is 32. So the fifth root of 32 is 2. On my calculator, I'll do fifth roots just like fourth roots. I'll hit the shift and then the X with the square exponent, type in the number 5 for the index, kind of arrow over, type in 32, and it tells me that that equals to 2. Not that you can see the 2. So the beginning problems in this section are just a bunch of problems that it'd be nice to be able to do without your calculator, but your calculator is not going to let you down, because the first 30 problems only have numbers in them, and if we have a radical or a root, and we don't have any variables or letters, my calculator would chew those right up. So I'm going to do each one of these by hand and then by my calculator for the even ones between 1 and 30. And it would be nice if you knew how to do most of these without a calculator. So the first problem I see is the square root of 16. That's asking the question, what number times itself twice is 16? The answer is 4. If this was a test question, I would just write the number 4 down and be done. If I wanted to check, for my answer to a square root to be correct, I need to be able to take my answer, multiply it by itself twice, and that has to equal the radicand. And because that's true, my answer is right. On my calculator, I'd hit the square root button, type in the number 16, and hit equals. 4 is a little bit different. The negative in front of the square root means find the opposite of the square root of 36, or equivalently, multiply the square root of 36 times -1. The square root is kind of treated like a parentheses, and I do it before anything else. So if I was doing this by hand, I would think of this as -1 times the square root of 36. And I do square roots before multiplication. The square root of 36 asks me what number times itself twice is 36. That answer is 6. So this is really -1 times 6. And the whole answer to this equals -6. a little bit harder to check, because if I multiply negative 6 by itself, I only get positive 36. I can check that I did the square root right, because 6 times 6 is 36. I know I did the multiplication right. My calculator won't let me down, so I'll do this on my calculator. I hit the negative in the parentheses, type the square root key, type the number 36, and my calculator will understand what the answer should be, and it gives me the negative 6 just fine. Six has a number to the left of the square root, and that's not the seventh root. That's not written kind of up in the little cup. It's not kind of written as subscripted. It's written as the same font as the 25. And just like the negative sign in the last problem, this really means 7 times the square root of 25. When I see a number to the left of a square root that's not a root, not an index, should I say, then that number gets multiplied by whatever the square root equals to. In this case, I know the square root of 25 is 5, because the square root of 25 asks me what positive number times itself twice is 25. The answer to that is 5. So the whole answer to problem 6 is 35. Again, I can do this on my calculator. It's not terribly hard. I type the number 7. I don't need a times symbol, because if I type a number and have a square root symbol next to it, the times is implied. If I do 7 times the square root of 25, my calculator tells me that's equal to 35. Hey, I see a negative there. That's because my calculator's got dirt on it. Oh, that's a horrible place for dirt. I can't clean that right now, huh? Oh, gosh. That's not good. Clear. See, my calculator has this little dot there, which probably I got my marker on it. And it might make everything look like a negative, which is really horrible. So when I did 7 times the square root of 25, it's supposed to be positive 35. That little dot isn't a negative. I wonder what happened when I did the last problem. When I did negative square root of 36. Oh, the negative is definitely different. See, the negative is a little bit closer to the number. That's just a random dot. Maybe I'll get some rubbing alcohol or something and try to clean that, because it's a bad, really bad place for that dot. 8 asks me what number times itself 3 times is 27. The answer is 3, because 3 times 3 times 3 is 27. It'd be nice if you just magically knew that, because you knew some cubes. But if you don't, you hit your shift, your square root key, that allows you to do a cube root immediately, and you'd get to 3. If you wanted to, you could do it the other way too. You could do it this way. You could do shift and hit the X with the square key, physically type the 3 in, and then type the 27 in. So there's kind of 2 ways to do cube roots. But regardless, the cube root of 27 is still 3. I got tired of that orange marker. It wasn't dead, but I broke up this kind of raspberry-ish marker that I thought was kind of fun today. So I'm using it probably too much. 10 asks me the question, what number times itself 3 times is negative 125? That's the question that's asking. The answer is negative 5, because if you multiply negative 5 times negative 5 times negative 5, you get negative 125. So the answer to this is going to be a negative number. And I could know that without my calculator, but I teach, and I've done this chapter 30 times already, so it's not that impressive that I could know the cube root of 125 with a negative in front of it. But the answer is going to be negative 5, because negative 5 times negative 5 times negative 5 equals negative 125. And that's the question that this is asking. On my calculator, I would just probably go shift, hit the square root button to get the cube root, use the negative in the parentheses, type the number 125, and I get negative 5. So I won't be able to tell if these were test questions if you're relying on your calculator, or if you're just clever and you know radical, you know roots in your head or radicals in your head. It doesn't really matter. It's not that important. If you went to a school that made you learn squares, cubes, and fourth powers, then you'll have an advantage, but not a huge advantage because your calculator is a great equalizer here. If you're going up high in math, if you're going to be a calculus student, these are the kinds of problems we should just be able to do in your head because they're not really that hard. It just takes a little memorizing of squares and cubes. So, like if I was going on to calculus, I would probably have all these memorized. That 1 squared is 1, which means the square root of 1 is 1. That 2 squared is 4, which means the square root of 4 is 2. 3 squared is 9, so the square root of 9 is 3. 4 squared is 16, so the square root of 16 equals to 4. 5 squared equals 25, so the square root of 25 equals 5. 6 squared equals 36, so the square root of 36 equals 6. I'd probably know my squares up to 12. 7 squared is 49, so the square root of 49 is 7. All the way up to 12 squared is 144, so the square root of 144 equals to 12. If I'm going high in math, I should know those. For cubes, you should know maybe 1 cubed is 1, so the cube root of 1 is 1. 2 cubed is 8, so the cube root of 8 is 2. 3 cubed is 27, so the cube root of 27 is 3. 4 cubed is 64, so the cube root of 64 is 4. 5 cubed is 125, so the cube root of 125 is 5. Now we're getting to the point where it's silly to just not use your calculator. Probably the highest one I'd learn is 6 cubed is 216, so the cube root of 216 is 6. I don't know many fourth powers, but these were all things I would memorize if I wanted to do radicals without my calculator. I would know that for fourth powers, 1 to the fourth is 1, so the fourth root of 1 is 1. 2 to the fourth is 16, so the fourth root of 16 is 2. 3 to the fourth is 81, so the fourth root of 81 is 3. 4 to the fourth is 256, so the fourth root of 256 is 4. And the last one I really know, 5 to the fourth is 625, so the fourth root of 625 is 5. Again, my calculator will do every single computation that I just scribbled here. But like I said, if you're going high in math, these are just common. It really is common knowledge. For fifth powers, I don't know many. 2 to the fifth power is 32, so that means the fifth root of 32 is 2, and 3 to the fifth power is 243, so the fifth root of 243 is 3. That's really the only common fifth powers. So all these, if you knew these, you could blow through these questions a little bit quicker, but it's really, it's not that important. If you rely on your calculator, it's not going to let you down. For 12, it's pretty complicated because this is really asking me to do -1 times the cube root of -27. The cube root of -27, this asks me what number times itself 3 times equals -27. And because -3 times -3 times -3 equals -27, the cube root of -27 is equal to -3. So this whole problem can be written as -1 times -3, because I do the cube root before I do the multiplying by -1, or finding the opposite, which is the same as multiplying by -1. The answer to this problem is going to be 3. Again, I could be completely mindless and hit the negative in front of my parentheses, shift cube root key, and then -27, and my calculator will tell me that that's +3. So again, it's nice to be able to do these by hand, but if you're not getting much higher in math than college algebra, it's just not that big of a deal. 14 asks me what number times itself 3 times is 1. that's 1. So to do the shift cube root of 1, my calculator will tell me that it's 1 because 1 times 1 times 1 is equal to 1. 16's asking me to do the square root of a fraction. To do the square root of a fraction by hand, you have to do the square root of each number separately. I'll do the square root of 49, and whatever that equals to, I'll leave that number in the numerator because 49 is in the numerator. And I'll do the square root of 25, and whatever that turns into, I'll leave in the denominator. The square root of 49 is 7, because 7 times 7 is 49. The square root of 25 is 5, because 5 times 5 is 25. So the answer to that is 7 over 5. To do that on my calculator, it's not terribly hard. I hit the square root button first to get my square root activated. Then I hit my fraction key, so I get a fraction under the square root. Then I type 49, go down to the denominator, do 25. My calculator is going to tell me that this equals to 7/5. So this calculator is just, it's so nice. It's better than any calculator that I've seen for doing just about everything. It does fractions and square roots, radicals so nice that it makes this way easier than if you had some other sort of technology. There are some calculators that work backwards when you do roots or radicals, and they're really tough, and it's way easier to do them by hand than it is with certain calculators. 18, the cube root of a fraction, you have to do the numerator separate from the denominator. I'm going to do the cube root of 8 over the cube root of 27 if I'm flying without a calculator. The cube root of 8 asks me what number times itself 3 times is 8. Because 2 times 2 times 2 is 8, I'm going to place the cube root symbol with the number 2. The cube root of 27 asks me what number times itself 3 times is 27. Because 3 times 3 times 3 is 27, I'm going to write a 3 there. So that should equal to 2/3. We do it on my calculator. Shift in the square root key to activate the cube root, the fraction button, and then 8 over 27. And that equals the 2/3 that it's supposed to equal to. 20 asks me what number times itself 4 times is 81. The answer is 3, because if you multiply 3 by itself 4 times, if you go 3 times 3 times 3 times 3, because it equals to 81, the fourth root of 81 is 3. If you don't just know that, then you do in your calculator, you hit the shift key, the x with the exponent key that allows me to enter the index of 4, arrow over to get in under the radical to type the radicand of 81 in, and I see the answer is 3. So the fourth root of 81 is 3. (22) on my calculator might be tricky. There isn't a times sign between the 2 and the 81, but this means 2 times the fourth root of 81. In general, you might not know what the fourth root of 81 is, but we just did the fourth root of 81 on problem 20. So I know that the fourth root of 81 is 3. So this is 2 times 3. Always do radicals before multiplication. After I get rid of the radical, I can multiply and it turns into a 6. On my calculator, if I try to do this, if I go 2, shift, and hit the x with the exponent key, it messes me up. It puts the 2 as the index. So I have to separate the 2 from the radical, and I could do it with a parentheses or a times sign because this means 2 times. And I'm gonna do it with a times. I'm gonna go 2 times and then shift, and now I can type in the fourth root of 81. That's one way to defeat make the calculator do this correctly. Another way I see students do this correctly is to kind of go backwards. You could also do this. You could go shift and do the fourth root of 81 first, and then back arrow a few times, and then type the number 2 in. That's 2 times the fourth root of 81, just like it looks on the handout. And I can still get the 6 that way. So if you wanted to make it look just like the handout, you have to do the fourth root of 81 first. If you tried to do 2 and didn't put a symbol in between 2 and the fourth root, it makes the 2 the index. So what I just did again, I did shift x with the square, typed in 4 typed in 81, and then I'm just backwards, left, 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 left. Then I type the number 2 in. That will work. Similarly, hitting 2 and then times, shift, allow myself to type the 4th root of 81 in as well. They're both equal to 6, but you have to fight it a little bit. You can't enter the problem how it's written in the order that it's written. You either have to put a time sign or enter it backwards. 24 really means -1 times the 4th root of 81. The 4th root of 81 is 3, so this means -1 times 3. So this whole thing is equal to -3. This I don't know if I'll have to fight my calculator on. If I do negative and then shift, it didn't fight me. So I just typed the negative, and then I typed the thing to give me the 4th root of 81. So I'm able to, that's not confused by. I didn't have to do that backwards like I did the other one. I didn't have to enter the -1 times. A negative in front of the 4th root of 81 implies -1 times, and it gives me that -3 that I knew it had to be. (26) asks me what number times itself 5 times is -243. The answer is -3, because if I multiply -3 by itself 5 times, it will equal -243. I can show you if I did -3 times -3 times -3 times -3 times -3. Multiplying -3 by itself 5 times, I get -243. So I know that's the answer because that's the question that this is asking. 5th root means what number times itself 5 times is the radicand. To do this by my calculator, I'd get the 5th root in there. Under the 5th root, I use a negative in the parentheses and type the number 243, and I get -3. Again, if I'm doing these, every one of the first 30 problems, I would just write the answer down because I could do them all in my head. So it doesn't matter to me if you're resorting to your calculator or not. 28 wants me to find 3 times the square root of 49. There isn't a time symbol between, but it's implied. The square root of 49 asks me what number times itself twice is 49, which is 7. And the answer to this is going to be 21. So again, on my calculator, I type the number 3. I don't need the time sign. I get at the square root key, type 49, and I get 3 times the square root of 49 equals 21. It has that silly dot there that almost makes it look like a -21. It won't just, I wonder if it would come out with an eraser. No. It's even worse. Well, it's not worse, but so I'm just dealing with that dot. It doesn't come out with an eraser, which is unfortunate. The last problem in the first grouping is 5 times the cube root of 64. And then the second grouping just wants me to use my calculator and round. So again, the cube root part wants what number times itself 3 times the 64. And that's 4 because 4 times 4 times 4 equals to 64. So if I was doing this without my calculator, I know that this is 5 times whatever the cube root of 64 equals to. The cube root of 64 is 4 because 4 times 4 times 4 is 64. My answer to this problem is going to be 20. Without being able to do it by hand, I go 5, shift, cube root, 64, and my calculator will kick me back that 20 just fine with that dot. That's not correct. Okay, 31 through 42, I had these written when calculators were hard to use, and the first 30 problems I had my students do by hand because calculators when I wrote this material a few years ago just weren't that easy to use, so we did all those by hand, but now our calculator will work. These problems, I'm asked to round to 4 decimal places, and they're purely calculator problems. So the first problem I see here, 32, if I do the square root of 6, my calculator all of a sudden says this is the square root of 6, and it doesn't give me a decimal. But the instructions imply I want a decimal answer. If your calculator does this, to get the decimal answer, you hit the key right above the delete, right above the cost, that SD key. If I hit the SD key, this tells me this is 2.44948. To round to 4 decimal places, I look at the number in the 5th decimal. If that number is 5 or bigger, I round the 4th decimal up. If it's 4 or less, I don't change the number in the 4th position. So I'm only showing 4 decimals. The first 3 decimals are 4, 4, and 9. I have to decide if that 4 is going to stay a 4 or if it's going to round up to a 5. It's going to round up to a 5 because the number after the 4 is 5 or bigger. So I'm going to write that for problem 32. For 34, I'm going to use my calculator again. I'm going to go 3 times the square root of 5. My calculator tells me that that's 3 square root of 5. I hit the SD button, and I get 6.70820. I look at the number in the 5th decimal place, and it tells me whether to leave the 4th decimal alone or round the 4th decimal up. Because that number is not big enough, it's not 5 or bigger, I'm going to leave the 2 alone and not round it up. And I'm going to write 6.7082 for a 4 decimal rounding of that, problem 34. 36 wants me to do the cube root of 12. So shift cube root of 12. And for cube roots, my calculator automatically gives me decimals. It does some fancy things with square roots that are going to be really nice when we get into the next few sections. So same deal, I'm asked to round to 4 decimals. I look at the number in the 5th decimal place, and it tells me whether to leave the 4th decimal alone or change it. The 4th decimal is a 4. It's either going to stay a 4 or get bumped up to a 5. Because the number after the 4 isn't 5 or bigger, I'm going to leave it a 4. And I'm going to write 2.2894 for problem 36. 38 is a 4th root, so I hit shift 4th root of 20. And I see 2.11474. Again, I look at the number in the 5th decimal place, which is a 4, and it doesn't tell me to round up because it's not 5 or bigger, so I'm going to leave that 7 alone. And in for our answer, I'm going to write 2.1147. $40 and 42 on a lot of calculators would be really hard. This calculator is not so hard. If I want to do this without the time sign, I have to do it backwards. I have to do shift 5th root of 40 and then left, 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 and type the number 3. Doing that, I get 6.27383. The other way to do this is I could have did 3 times key, shift, get the exponent, so I can do the 5th root of 40. It's still going to give me the same number. This is also an instance where I'm not rounding the 8 up. The number in the 4th decimal place is the one that could change, but it's not going to change from its 8 because the number after the 8 isn't big enough to force it to round up. And the last one in this grouping, 4 plus 3 square root of 6 is 4 plus 3 square root of 6. Hit that SD button. I get 11.34846. I look at the number in the 5th decimal place. Because it's 5 or bigger, 6 is 5 or bigger, I'm going to round that 4 up to a 5. I'm going to write 11.3485 for my answer to 42. All right, the next problems are semi-important, but but not directly on the test. So problem 43 says fill in the table. I somehow deleted the function when I made this fancy. Fill in the table. I don't know if it asked me to sketch a graph or not. Let me check here. If it actually asked me to sketch a graph, I think it might, but it may not. I know it asked me to fill in the table and find the domain. Of the function. The finding the domain is the important thing. And from the table, we should be able to find the domain. I'm just looking at the problem real quickly because I deleted the instructions to see if it asks me to sketch a graph. I almost don't think it does. I think I gave you the graph as a little bonus. Exactly. So it says use your calculator to fill in the table and then state the domain of the function. I was nice in that I used my graphing program that I got free online and I sketched a graph. So I'm going to first find the domain from the graph and show you how the domain from the graph matches up with the domain from the table. So I'm only doing domain, not range. I look at this graph. It has a solid period here. I should have labeled this as the point 30. And off to the right, it doesn't end. It goes on forever. It winds up at the far right edge of the x-axis and the top of the y-axis. If I wanted if I gave you a graph of this function and I asked you to find the domain, it's going to be real easy, because to find the domain from a graph, you need to find the point that's most left and its x, and the point that's most right and its x. So the domain of this function, which is really the reason I did this whole problem, the domain is going to be the interval from 3 to infinity. I'm going to show you how to do the table and how to interpret the table to find the domain. So to fill in the table, I have to find h of 6. I'm going to do h of 6. So for the first line of my table, I'm going to find h of 6, which is the square root of 6 minus 3. And when I do that on my calculator, I'm going to go square root of 6 minus 3. And my calculator tells me square root of 3. I'm going to get a decimal because it's easier for me to plot decimals. I'm going to 1.73. So the first point that if I was graphing without my program, I'd plot the point here. This apparently is the point 6, 1.73. Now I'll do the same for 5. I'm going to find h of 5, which is the square root of 5 minus 3. So if I do shift, oops, I don't need shift. If I do square root of 5 minus 3, I get square root of 2. Make it into a decimal, I get 1.41. And that would be this point right here. This is the point 5, 1.414. The next thing, if I plugged in 4, I'll get h of 4 equals the square root of 4 minus 3. This is the first one I don't need my calculator for, because I can subtract the 4 minus 3 and get 1. The square root of 1 is going to be 1. If I did this on my calculator, did the square root of 4 minus 3, my calculator is going to tell me that it's 1 anyways. So that's going to be this point, which is the 0.41. And then the next one, if I do h of 3, that's the square root of 3 minus 3. That's the square root of 0. That asks me what number times itself 2 times is 0. And that answer is 0. Again, if I did it on my calculator, the square root of 3 minus 3 equals 0. Something bad's going to happen for the next two problems, or next two parts. If I do h of 2, I get the square root of 2 minus 3, which is the square root of negative 1. this asks me the question, what number times itself twice is -1? If you multiply any two numbers by themselves, if I thought the answer was 1, it's not 1 because 1 times 1 is 1, not -1. If I thought the answer was -1, I'm wrong because -1 times -1 is also +1. There's no two numbers I can multiply to get a negative unless one of them was positive and one of them is negative. So when I do this on my calculator, it's going to give me, it can't be done. When I do the square root of 2 minus 3, I get math error because there is no number that you can multiply by itself twice to get a negative number. And this is why on my graph, there's no graph right here because I get an error. And actually, if you've taken some math, higher math, this actually equals to I, an imaginary number. Doesn't show up on a graph because my graph doesn't have imaginary numbers, but that's too advanced. That will come in section 410. We'll learn about i's. If you already know about i's, it's nice, but they don't come up yet. The next point I want to do is h of 1, which is the square root of 1 minus 3, which is the square root of -2. This is also going to give me an error because no number times itself twice is going to give me a negative number unless it's imaginary. So when I do this on my calculator, I'm going to get an error as well. So if I did clear square root of 1 minus 3, I get the same math error. So it will turn out that every number to the left of 3, if I did the next number, I'm going to get an error for all of these. And so when my computer sketched a graph, it knew the graph wasn't going to exist to the left of 3. So from the table, I would find the domain by looking at where my y's exist, and my y's only exist from x equals 3 on. So the domain of this is 3 to infinity. You could see from the graph more clearly that the domain is 3 to infinity. From the table, you could see the break in the table. At 3, my y is 0, but less than 3, I get errors. In general, to find the domain of a square root, I don't need to do a table. I don't need to have a graph. There's an algebraic strategy that I can use to find the domain of any square root, and that's really easy. So I should mention it now because it's important. So I've completed this problem because this problem, all it asks me to do is fill in the table and find the domain. You don't have to sketch a graph, although it might help you visualize the domain a little bit better, but you don't have to. But in general, like this problem, h of x equals the square root of x minus 3, there is a way to find the domain of any square root function. By doing algebra. It isn't really necessary to make a table of values or sketch a graph to find the domain of a square root function. Ugh, this is getting insanely long. The algebra is just to solve the radicand, or what's under the radical, greater than or equal to 0. The algebra to find the domain of a square root function, not a cube root function, is you solve the radicand, that's what's under the radical, greater than or equal to 0. So I'll give you a second to digest this. So the whole reason I did problem 43, which is actually an odd problem, is we need to have the ability to find the domain of a square root, and I wanted to give you a few visual kind of prompts. This table might help you see why the domain is 3 to infinity. This graph should help you see why the domain is 3 to infinity. But I don't need the table, I don't need the graph to find the domain of any square root. And the whole reason we're doing problem 43 is because I need to be able to find the domains of square roots for the test. So if I want to find the domain of this, I'd go like this. To find the domain without creating a table, without sketching a graph, I'm going to take the radicand, which is what's under the radical, set it greater than or equal to 0, and solve for x. To solve this for x, I'm just going to add 3 to both sides. On the left side, the 3's will cancel. On the right side, 0 plus 3 is 3. So it would be correct to say the domain of this is x is greater than or equal to 3. And that's the same as this interval from 3 to infinity, because this means any number 3 or bigger. Greater than or equal to 3 means any number 3 or bigger. Alright, so I'm going to do problem 44, do exactly the same thing. I'm going to fill in the table, show you how the table could be used to create the graph that I gave you, that I copied from my computer. You show how the table shows the domain, show how the graph shows the domain, and show you how to find the domain without the table, without the graph, which is ultimately the skill that we're going to need. So 44 gives me the function the square root of x minus 2. It wants me to fill in the table and sketch a graph. So first of all, I don't need this. It just wants me to fill in the table and find the domain. This is the graph. Super easy to find the domain of a square root if you have the graph. So if I wanted to just find the domain, this is the beginning of the graph. It doesn't extend beyond this, but it goes off to the right forever. The domain of this, I need the far left point and the far right point. The domain of this is going to be any number bigger than 2 off to infinity. You'll see in the table that anything after the 2 in the table, I'm going to start getting errors. So if I fill in this table, the table could help me create the graph. First thing I would do is find h of 6, which is the square root of 6 minus 2. I don't need my calculator, but I like using it, so I'm going to go the square root of 6 minus 2. My calculator tells me that that's 2, because that's the square root of 4, which is 2. So on my graph, that would be this point, the point 6, 2. When I do h of 5, I get the square root of 5 minus 2. I have to hit my SD button now. That gives me 1.73. On my graph, that's this point right here. This is the point 5, 1.73. When I do h of 4, I get the square root of 4 minus 2, which is 1.41. That's this point here is the point 4, 1.41. When I do 3, I get h of 3 is the square root of 3 minus 2. Square root of 3 minus 2 is going to be 1, because this is the square root of 1, which is 1. That's this point, 3, 1. When I do 2, I get h of 2 is the square root of 2 minus 2, which is the square root of 0, which comes out to be 0. On my calculator, the square root of 2 minus 2 is 0. That's that point. The next 2 points is where I'm going to get my errors. When I do h of 1 is the square root of 1 minus 2, I'm going to get the square root of negative 1. So if I do the square root of 1 minus 2, I get an error. So there's no graph here. I get an error there. When I do h of 0, I get the square root of 0 minus 2, which I also get an error. So I've done what I came out to do. I filled out the table, I wrote the domain, and I can see why the domain is what it is, because any number that's greater than or equal to 2, I got a y that was plottable, or existed. I mean, some may have been some decimals, but I could find all those points on a graph. Once you plot the points, you just connect them to make the graph. And I saw that numbers that were less than 2 started giving me errors. The graph didn't exist there. So I filled in the table. The table pointed out to me that domain was numbers 2 and bigger. The graph also tells me that. If I wanted to find the domain via algebra, it's going to match up perfectly. The algebra to find this domain without having to make a table or sketch a graph, you just take the radicand x minus 2 and set it greater than or equal to 0. And I add 2 to both sides. This would give me x is greater than or equal to 2, which is the same as 2 to infinity. They both say this is any number bigger than or equal to 2. This is any number between 2 and infinity, which is the same as bigger than or equal to 2. So for the domain, both of these would be correct domains. They're equivalent ways of saying the same thing. 45 and 46 give me cubed roots, which are quite different than square roots. I'm going to do the same thing. I'm going to take my graph and find the domain from it. I'm going to see how that matches up with the table, and I'll talk about the algebra to find the domain. So you're not given in the handout the domain of the graph of this, but if I gave you this graph, you should be able to use this graph to find the domain. You'll notice that the graph extends to the end, the far left and the far right edge of the coordinate system, which means it needs to be extended. This graph, it would extend down to the bottom of the far left edge of the x-axis, the bottom of the y-axis, and it would extend up to the far right edge of the x-axis, the top of the y-axis. So this is the kind of thing that in chapter 2 we found the domains from. If I want to find the domain from it, I need the x-coordinate of the far left point and the x-coordinate of the far right point. So for this problem, the domain of the graph is negative infinity to infinity. Let me do the table now. First I'm going to do h of 6 is the cube root, not square root, of 6 minus 3. And I'm going to do this on my calculator. So shift cube root of 6 minus 3. I get 1.44. On my graph, this is the point right here that I just found. It's the point 6, 1.44. For h of 5, I'm going to do the cube root of 5 minus 3. So shift cube root 5 minus 3, and I get I'll say 1.26. On my graph, that's this point right here. This is the point 5, 1.26. H of 4 is the cube root of 4 minus 3. That's the first one I could do without my calculator, because that comes out to the cube root of 1, which is 1. But I'll be lazy and do it on my calculator. Cube root of 4 minus 3 comes out to be 1. That's that point right there. That's the point 41. The next one, h of 3, is the cube root of 3 minus 3, which is going to be the cube root of 0, which turns out to be 0. So again, shift cube root 3 minus 3 on my calculator comes out to be 0. That's that point right there. That's not the left edge of the graph, so 3 doesn't belong in the answer to the domain. If I do h of 2, I get the cube root of 2 minus 3, so shift cube root 2 minus 3, that gives me negative 1. So that gives me that point right there, which is the point 2 comma negative 1. If I do h of 0, I get the cube root of 0. If I do h of 1, I get the cube root of 1 minus 3. So shift cube root 1 minus 3. That's negative 1.26. So I get the point 1 comma negative 1.26. And then the last one I decided to do, because eventually you have to stop, is the cube root of 0 minus 3. And that gives me negative 1.44, which is that point there. And then my computer just connected these points. It actually just finds more points than I've found, and it just connects them. So from the table, you should be able to see that the domain of the square root problem I did in problem 44, the domain of the square root problem I did in problem 43, the table's very different. If you look at 43, the domain was 3 to infinity because after 3 I started getting errors. In 44, the domain was 2 to infinity because after the 2 I started getting errors. In my problem 45, so the square root domain 3 to infinity, square root domain 2 to infinity, cube root, there aren't any errors, so my domain isn't restricted. It's an unrestricted domain of negative to positive infinity. And that's going to be the case in general. In general, there's the domains of cube roots. I won't need algebra to find them. It's just going to be negative to positive infinity. So if I wanted to compare cube root versus square root, the domain of a cube root is usually, and always in our class, negative infinity to infinity, and no algebra is needed to find the domain of a cube root. I don't need to make a table. I don't need to sketch a graph. If I see a cube root, in general, I can bank on the domain being negative to positive infinity, which is the same as all real numbers. For a square root, for our class, the domain is usually x greater than, this isn't even spelled right, usually x greater than or equal to some number, which is the same as some number comma infinity. And there's algebra. The algebra that's needed is to find what's under the radical, find out where it's greater than or equal to 0. So the reasons problems 43, 44, 45, and 46 exist are just to help you differentiate between cube roots and square roots and understand why the domains of cube roots don't have any restrictions, but the domains of square roots do have restrictions. The domains of square roots have restrictions because not all numbers have square roots. The square root of a negative number doesn't exist. So square roots domains are restricted. But because the cube root of negative numbers turn into negative numbers, cube roots have unrestricted domains. I'm going to do 46, and then I'm going to skip to the problem 75 through 79 at the end of the section because they tie in with these problems perfectly. So same deal here. I'm going to fill in the table and find the domain. Immediately, I see this as a cube root. If I didn't have any of this and I was asked to find the domain, I know that for our class, the domain of any cube root doesn't require algebra. It's negative to positive infinity. The graph for this is essentially the graph of the last question. It's similar. It's a little bit different. But you can see that this graph exists all the way to the left, all the way to the right. It doesn't have a starting or stopping point. The domain is negative to positive infinity. I'm going to go ahead and fill in my table. First thing I want to do is h of 0, which is the cube root of 0 plus 3. So shift cube root 0 plus 3. That's 1.44. On my graph, that's this point right here. That's the point 0, 1.44. And then I'm going to do h of negative 1 equals the cube root of negative 1 plus 3. I get 1.26. So negative 1, 1.26 is that point. That's the point negative 1, 1.26. Now I'm going to do h of negative 2, which is the cube root of negative 2 plus 3. So shift cube root negative 2 plus 3, and I get 1. That's this point right there is the point negative 2 comma 1. H of negative 3 equals the cube root of negative 3 plus 3. So shift cube root negative 3 plus 3. I get 0, so that's the point negative 3, 0. It's an intercept, but it's not a feature of my domain because it's not the start, it's not the edge of the graph. It's not like a break in the graph or the beginning or the end of the graph. When I do h of negative 4, I get the cube root of negative 4 plus 3. Shift cube root negative 4 plus 3. I get negative 1 for that. That's this point, the point negative 4, negative 1. H of negative 5 equals the cube root of negative 5 plus 3. I get negative 1.26. That's that point right there. That's the point negative 5, negative 1.26. And the last one, h of negative 6, is the cube root of negative 6 plus 3. Shift cube root negative 6 plus 3. I get negative 1.44, which is that point there. And then I could just connect the points if the graph wasn't done for me. And the reason I wanted you to fill out the table is so that you can see there isn't any reason to have a restriction in my domain, because no matter what number I plug in for x, I can get a y. I'm not getting any errors. And that's why the domain of cube roots are negative to positive infinity, and I don't have any algebra to find the domain because there aren't any y's that give me errors. Whereas square roots, because the square root of a negative number is an imaginary number, their domains are restricted to exclude the numbers that when you plug those in for x cause a negative to come under the radical. So I'm skipping all the way down, and I'm going to do a lot of the odd and the even problems just to hammer these down because they're easy to do, and you need to do them on the test. So each of these problems relate to 43, 44, 45, and 46. They give me a function that's a square root or a cube root, want me to find the domain. 75a is the square root. To find the domain of any square root, I take what's under the radical and set it greater than or equal to 0. Doesn't matter if the function's called f. I'm not even going to show that in my answer. So for an answer to 75, part A, it would be correct to say the domain is x is greater than or equal to 2. If you want to, that's the same as the interval from 2 to infinity. And that tells me if I plug a number like 1 in, I'll get an error. If I plug in 0 for x, I'll get an error. If I plug in negative 1 for x, I'll get an error. But if I plug in 3 for x, 4 for x, 5 for x, 6 for x, I won't get errors. That's why the domain is restricted. Any number less than 2, if you plug it in for x, like if I plugged in 1 for x, if I did the square root of 1 minus 2, I'll get an error. So the domain tells me if I pick a number 2 or bigger, like if I pick a number like 7, I do the square root of 7 minus 2, not going to get an error. I get something I can make a decimal into. Part B, it's a cube root. The domain for it is going to be negative to positive infinity. There's no algebra for the domains of cube roots. No matter what number you pick, if I plug it in for x and I simplify it, it's going to come out to either a nice integer or a decimal, but I won't get any error messages. 76 is essentially the same problem. In fact, the next 4 problems are all essentially the same. 76, part A, wants me to find the domain of a square root. I don't need to sketch a graph. I don't need to make a table. To find the domain of any square root, I take the radicand and set it greater than or equal to 0, and I solve that. And each of these are just simple one-step solutions. So the domain answer for problem 76a, you could either write x is greater than or equal to -2, or you can write the interval from -2 to infinity. They're both correct answers. There's not one that's better than another. And I'd probably just leave my answer like x greater than or equal to -2 because that's what the algebra shows me. For part B, it's a cube root. Nothing bad can happen with a cube root. There's no algebra to do to find its domain. I'll save problem 77 for you, and I'll do 78. So 77 is going to be a homework question. 78 is going to have fraction answers for one of the parts, but it won't be so bad. So 78a, find the domain of a square root. I take the radicand, set it greater than or equal to 0. I solve for x. This is going to be a two-step problem. I'm not going to need to switch the direction of the inequality. When you have greater thans or less thans, if you have to divide or multiply by a negative, you switch the sign. If this 6 was a negative, and I had to divide by a negative, I'd switch the signs. But it's not. It's positive, so I keep the greater than a greater than. I reduce the fraction. The domain has a fraction in it, but it's not bad. So for 78a and b, a has algebra, it's the domain of a square root. Can be written with a greater than or equal sign, or it can be written as an interval. Part B, it's so tempting to want to do algebra, but there's no algebra necessary to find the domain of a cube root. All cube roots in our class will have domains of negative to positive infinity. I'd have to do something really evil, like make a fraction with a cube root in the denominator to make it an exception to that rule. So I can make horrible exceptions, but they don't come up in this class at all. And I don't really think they even come up in our college algebra course. It's not that big of a deal finding the domain of a cube root. It's not the most important skill, but it comes up again in college algebra. 79, the domain of any square root. You take what's under the radical, set it greater than or equal to 0. And this is one of the problems that's so easy that it's hard. When I set the radicand greater than or equal to 0, I have my answer. So for 79, I can say the domain is x is greater than or equal to 0 or 0 to infinity for part A. For part B, I so want to do algebra, but there is no algebra necessary. Every cube root, unless it's really something really odd, has a domain of negative infinity to infinity. If you do some algebra, the algebra will likely find the x-intercept. And in a cube root, the x-intercept isn't at the far left edge or the far right edge of the graph, and it doesn't belong in my answer. Okay, there's two styles of problems left, and I'm going in a backwards order. I'm going to do 59 through 74, and if you stop the video after 59 through 74, it's not going to hurt you at all. After I do 59 through 74, I'll talk about 48 through 58, which are the problems that I've skipped over so far. There's some subtleties in those problems that involve using absolute values that just aren't really important. They're theoretically correct, and it's maybe nice if you're going high in math to understand some subtleties, but I've had a disastrous time explaining the theory in the technical way that those problems introduce the theory. So what's test-worthy is everything I've done so far in 59 through 74. In this section, the problems between 48 and 58 are not on the test. They're not horribly important. They're just some theory. So numbers 48-58, they're absolutely okay to skip. But if you want to watch me do these in the video, I'll teach you a subtlety. But then again, it might be more the subtlety, I think, is more confusing than it's worth, and I'm tempted just not even to talk about that subtlety. Maybe I won't even talk about it. I'm really debating because, like I said, I've had a disastrous time talking about a subtlety that that has to do with absolute values. That just it's not something we do in most higher classes. In college algebra, the subtlety won't come up. So 59 through 74 has to do with taking square roots and cube roots with letters. I should talk about that for a second. So how about radicals and variables? Let me do a nice one, like the cube root of x to the 6th. To do the cube root of x to the 6th, this asks me what times itself 3 times equals x to the 6th. Well, the answer is x squared, because if I multiply x squared 3 times, when you're multiplying with the like bases, you add the exponents, and x squared times itself 3 times is x to the 6th. How do I get x squared for an answer? You divide the exponent by the index. So for variables, if you can divide the exponent by the index and not get a decimal or a fraction, that's the way we're going to reduce radicals with letters. So this problem, I'm going to say this is x to the 6th divided by 3. 6 is the exponent, 3 is the index. I drop the radical when I do that. 6 over 3 is 2. If I did something like this, the square root of, I'll continue with x, the square root of x to the 6th, same number in some sense, but different. This asks me what times itself 2 times equals x to the 6th. The answer is x cubed, because x cubed times itself 2 times. You add the exponents and you get x to the 6th. Just like the problem above it, I'm going, if the exponent and the index, if you can divide them and not get a fraction, that's how I want to reduce the radical. Remember at the beginning I said in square roots there's an index of 2 that's assumed but not written. So to simplify this, I'm going to divide the exponent 6 by the index 2 and get x cubed. That should be enough for us to do the next problems that are test worthy. 60 is a combination problem. It has the square root of 16b squared. I'm going to do this like it's 2 separate problems. I consider this the square root of 16 times the square root of b squared. The square root of 16 I could actually use my calculator for. It's going to be 4. The square root of b squared, I'm going to divide the exponent by the index. So I'm going to go b to the 2 over 2 power. And I'm trying to color code the 2 so you know that this black 2 is the exponent, this pink 2 is the index. For an answer, I'm going to divide that exponent. I don't need the time sign between the 2. I could write 4b to the 1st power, because that is what happens when you divide the 2's. But the best answer is just 4b. Problem 62. It's a square root and a letter. There's an index of 2 that's implied. When I simplify a radical with a letter, I attempt to divide the exponent by the index. If this was like 10 divided by 3 and you got a fraction, then we do something different, and we learn that, I believe, in the next section. But for this problem, the answer to this is just y to the 5th power. So it's real easy to in fact, letters are easier to deal with than numbers. Because I just divide. I don't have to have any special knowledge. 64 wants me to do the square root of x to the 12th. Again, in a square root, there's an implied index of a 2. So this is going to be x to the 12 over 2 power, which is x to the 6th. 66 wants me to do the cube root of y to the 12th. So that's going to be y to the 12 over 3 power. And the answer to that's going to be y to the 4th. 68 wants me to do the 4th root of z to the 24. Again, if you can divide the exponent by the index and you don't get a fraction, that's the way we're going to reduce. So this is going to be z to the 24 over 4. I don't need a calculator for that, but I'm wearing out. And 24 over 4 is 6. So my answer to 68 won't have a radical anymore. It's just going to be z to the 6th. 70 is the square root of a fraction. So I need to do the numerator separate from the denominator. The numerator wants me to do the square root of x to the 8th. For the x to the 8th, I divide its exponent by 2. In the denominator, the square root of 16 is 4 because it asked me, well, I can do it on my calculator. Square root of 16 is 4. In the numerator, I'm going to write x to the 4th. This isn't reducible. You can't cancel the 4s. You can't cancel a letter with an integer. And that's just the answer to 70. 72, I'm going to treat like 4 problems. I'm going to do the 4th root of 256 times the 4th root of x to the 4th in the numerator. And in the denominator, I'm going to do the 4th root of y to the 8th times the 4th root of z to the 12th. I don't really need these time symbols. So 4 different problems. First, 4th root of 256. So shift 4th root 256. That turns into a 4. So in the numerator, where the 256 is, I won't have a radical. I'm just going to have the number 4. Don't really need the times sign, but I can have the times sign if I want it. For the x, I'm going to get x to the 1st power because I'm going to divide the exponent in the index. For the y's, I'm going to get y to the 8 over 4, which is going to be y squared. And the z, I'm going to get z to the 12 over 4, which is z cubed. So my answer in the numerator, I'm going to have a 4. And x to the 1st, I don't need to write the exponent of 1. In the denominator, I'm going to have a y to the 2nd, z cubed. I don't need the time sign between the 4 and the x, nor do I need the time sign between the y and the z, the times implied. 74, I have to treat this as -1 times, and then I'll do the square root of 9, the square root of x squared, the square root of 49, and the square root of y to the 4th. So this is going to be -1 times square root of 9 is 3. For the x, I'm going to divide the exponent by 2 and get x to the 1st. In the denominator, the square root of 49 is 7. For the y, I'm going to divide its exponent by 2 and get 4 over 2, which is 2, which is y squared. And now I have flexibility doing the multiplication with the -1. I'd probably multiply the -1 in the 3 and leave that a -3. But I could just leave the negative to the left. So I could write -3x over 7y squared, or I could leave the negative to outside the fraction and just make the 1 disappear. Both of these are good answers. I'd probably have that for my answer, but most authors would probably write that, so there isn't one that's kind of noticeably better than the other. So that's all we're responsible for. I feel afraid to lecture on 48 through 58 with the idea maybe it would confuse you. If you have the desire to see 48 through 58 and to get the theory explained, visit me in my office and I'll sit down and do all the problems with you, tell you about the subtleties, how when we're doing square roots with letters that sometimes it's appropriate to use absolute values. Again, it's just not that important. We 99.9% of the time bypass that subtlety, and the 0.1% of the time that it comes up, it's not worth in an intermediate algebra class dragging you through that mud for something that just doesn't come up that often. So go ahead and skip 48 through 58. If you have the desire to learn those, come visit me and I'll show you how to do them. But they're not going to be on the test. If you could do the last group of problems that we just did, those definitely will be on the test, so you need to get good at those. Okay, so we're getting closer to the halfway point in this chapter, and more often than not, I give two 50-point tests in chapter 4, one that covers the first 5 sections and the second that covers sections 6 through 10. So expect a test worth 50 points after you get through section 4-5.